So, I'm going to be talking a little bit about the nucleus and its structure. I'll start with a little bit of the history, and I hope that you gain a better appreciation for how cool the nucleus is. So, to start, we know that several different models of the nucleus have been presented over time. Originally, John Dalton introduced the atom. J.J. Thomson then discovered electrons. And then shortly after, they said, okay, well, there's got to be positive charge somewhere. So this plum pudding model was discovered. But Ernest Rutherford, finally, in his gold foil experiment, discovered that there's something in the middle of an atom. He shot alpha particles at this gold sheet, and basically stuff came back at him. Something got in the way. And he concluded there's something in the middle of an atom called the nucleus. At that point, we didn't know that there were protons and neutrons, but that he disproved the plum pudding when actually he was ironically trying to find that and to prove the plum pudding was real. But he found that it wasn't. And later on, James Chadwick found and discovered the neutron. Basically now we know that there are protons and neutrons in a tightly packed ball called the nucleus. And we know that they are spherical in nature. I'll talk a little bit more about that and how we know that they're spherical, which is kind of crazy that we can figure that out. But we do, and that's kind of what we know now. Comparing the two, we call protons and neutrons nucleons because they are in the nucleus. Comparing the two, we know that protons have a positive charge, neutrons have a neutral charge, and neutrons are a little bit bigger than protons as far as the mass goes. We're using a Dalton scale here, which is AMU, or U for shortened, basically atomic mass unit. This atomic mass unit, you're probably wondering, well, why aren't they 1? Why isn't a proton 1 and neutron 1? The scale U was actually originally made so that a carbon atom would have exactly 12 U. And you think, well, it has 6 protons and 6 neutrons, right? So it still should be 1. But actually, there's something called a mass defect that Einstein proved with his formula E equals mc squared. Basically, the energy used in creating an atom that needs to create substance is equal or has some decrease in mass. So this decrease in mass equals the energy required to make the atom divided by the speed of light squared, E equals mc squared. So there's some tiny mass lost when nuclei are made. So protons and neutrons individually have a tiny bit higher mass than when they're together. So we know that 1U is a 12th of a carbon atom, or when 6 protons and 6 neutrons form carbon, its U is 12, right? And that's kind of where that came from. We see the conversion down here into kilograms, and there's a diagram in the textbook that also has some more conversions there. The next slide will also talk a little bit about a more important for physics conversion into mega electron volts. Quickly comparing to electrons, remember that it's not actually a nucleon because it's not the nucleus. Protons and neutrons are giant, very large compared to electrons. So we know from this that the mass or the bulk of the mass of an atom is in the nucleus, which is pretty significant as well. So one thing, for example, if we want to deal with energy and things like that, we need to move this AMU into another conversion. There's actually a conversion to mega electron volts, which is really useful when we're solving problems like finding the rest energy of a proton. So we can change the mass of it from U into mega electron volts using this conversion and find the rest energy of a proton to be about 938.27 mega electron volts. We can see here that the C squareds cancel out. So this unit's really helpful when we're dealing with energy and doing calculations there. So some really useful conversions. Basically, we see that protons and neutrons bulk of the mass, and really that they're very tiny, as you can see here by the kilogram conversion. So what does that matter? what's really cool is that the nucleus tells us the identity of things. Any atom has an identity because of its nucleus, its protons and its neutrons. We know this, and we can see examples of this from the periodic table, right? You've probably seen something like this where X is the element, A, Z, and N. A is the nucleon, or the mass number of nucleons, right? Total nucleons. N is the number of neutrons, and Z is the number of protons. If we have the same Z and different N, we have what's called an isotope. And since a lot of these are solvable and related, we sometimes see it in this form where we know the element and we have its total mass number. Then from the periodic table, we can find the number of protons, subtract these two, and get the number of neutrons. So basically, all the information and what's really important about the identity of atoms can be displayed in a notation like this. For example, and you can pause the video and do this on your own, what does this 14C mean, right? So first, find the element name. You can pause it and figure it out, right? We know that it's carbon. Number of protons, you can pause and figure it out. From the periodic table, we know that it's 6, and then you can do the rest and figure out its name. Number of neutrons, you subtract and find 8, and then we know that this is then carbon 14. You actually say it in reverse when we're naming isotopes like this. So really cool that we can, all of this has to do with the structure of the nucleus. Everything here, right? The number of protons, neutrons, its name, the isotope that it is, everything comes from the nucleus, which is really neat. So we know that protons and neutrons exist. We know that they have masses that are the bulk of the mass. We know that they're in the center. And in the beginning of the video, I said that they are spherical in nature. Really? How do we know that? Really, we know that because, and the biggest evidence is that it's from the radius of the entire nucleus. This is the formula for finding the radius of a nucleus of an atom. R naught is a constant. A is the mass number. Remember, the mass number is the number of nucleons, protons, and neutrons combined, raised to the 1/3 power. So we can see, since nuclei are spherical, we can see that R cubed and A, well, we know that R cubed and A are proportional if you cube both sides. Since they're spherical, the volume of the sphere is V equals 4/3 pi R cubed. We can see that V is directly proportional to A. That is, the volume of the nucleus is proportional to the number of nucleons, or protons and neutrons, in it, which is really cool. Evidence that protons and neutrons are spherical in nature because a group of them together form a sphere, which is pretty neat, that we can kind of derive that. Again, breaking the nucleus down, we see that they are individual parts and they really are spheres, and here's the evidence. So here's kind of a put it together problem that you might run into. First find the radius and then find the density of a nucleus. I'll explain why I put no way there at the top here soon. You can pause the video here and then I'll run it through quick. So pause it and try to figure it out. So here's the formula for the radius. Here's the formula for density. Remember volume. We know that it's a sphere. So we can find the density to be this 0.138 U per femtometer cubed. Remember, femtometer is 10 to the negative 15th meter. Again, that conversion into kilograms, we find that the density of a nucleus is 2.29 times 10 to the 17th kilograms per meters cubed. That is insane. No way. That means that all these tiny little particles are so close together that their density is this. 1 meter cubed of nuclear matter has that mass. That is crazy. To put that into proportion, it is 2 times 10 to the 14th power times greater than the density of water. That's 200 trillion times greater than the density of water, which is just nuts. Really, really fascinating that these little protons and neutrons are so tightly close together in the nucleus. And then you might wonder, well, how are they so close together? They're positively charged. Shouldn't they be repelling? That's a whole nother lesson about strong force, which I won't go into here. But basically, it is a marvel of the universe that atoms are the way they are. I was blown away. Really, really neat that protons and neutrons can be like that in the nucleus together. one more comparison here. If we had 1 cubic meter of nuclear matter, right? We don't have that much nuclear matter on Earth, but for example, in a neutron star, a meter cubed of a neutron star matter has the same mass as a cube of water, 61 kilometers on each side. That's crazy. The fastest people on Earth can run a marathon in 2 hours. So imagine a cube that takes you, 5 hours to run one length of it, filled with water, and that has the same mass, has the same mass as 1 cubic meter of neutron or nucleus matter. Really fascinating. I love the nucleus. I've learned so much about it. It's really fascinating that Rutherford discovered something so monumental, that the nucleus exists. It has protons and neutrons. They have the main mass of the entire atom, and their density, they're so tightly packed together. We know that they're spheres, and they have an insane density. Really cool stuff. And really, it's fascinating because we know this, can identify everything in the universe based on the number of protons and the number of neutrons that it has in its nucleus. Very significant, super cool. Hope you learned something. Thanks so much.